This is chapter 6.3. We're doing volumes of revolution, part A. So as a review, we need to look at volumes of prisms. So prism, you have a shape, and then you extend that shape. How do you find the volume? So volumes of prisms. So the basic technique, we want to find the area or how many squares are on the front of the prism. And how do we do that? What's that called? You should know that's called area. So we want to find the area of the front, and when we do that, it's telling us how many cubes are on the front face. You could do the bottom, the top, it doesn't matter, but basically how many cubes are on any particular face. If we look at that, the concept we have is area. What's the area of the front? Excuse me. And in this case, the area is going to be base times height, or length times width, whatever you want to call it. We can call this length, width, and we can call this depth, I guess, D, whatever you want to call it. The area would be length times width, and in this case, it's what, 5 by 4? So on the front, we know we have 20 cubes. Then the next thing we see, how many sets of those do we have? The depth, we have 3. So to find the volume, you take the area of the front times the depth. Well, the area in the front was length times width, and we found that to be 5 times 4, which gave us 20 cubes on the front, but then we said there's 3 sheets of that. The depth is 3, so we get a volume of 60. So that's the concept for a volume of a cube, or excuse me, a prism or a cube. You find the number of cubes on the front by finding the area and multiplying by how many sheets or the depth of that. So it works for any shaped prism. These are all examples of prisms here. And here we have 1, 2, 3, 4, 1, 2, 3, 4, 5. It's the same thing. We have 20. Ooh, the volume here is going to be hard. So the front has a volume, 20 cubes. And how many of those do we have? 1, 2, 3, 4, 5, 6 of them maybe. I'm guessing. This is not a very good picture. So I'm going to guess 120. Oh, wow. This one doesn't even have... Okay, this is going to be hard. Oh, they just cut it in half. So what's the area of the front here? It's going to be 1/2 base times height, which is 1/2 to 4 times the height. 1, 2, 3, 5. So the area is going to be 10. So I'm going to just make up my own because I can. So it looks like we have, that's not a very good drawing, 10 in the front, right? 10 in the front sheet, 3 sheets. So the volume would be 30. This is easier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12. Wow, I can't count. 1, 2, you got to see how many there are. 1, 2, 3, 4, 5, 6 maybe? So 12 times 6, 72. So we're just kind of giving you an idea of how this works. This one's easier. Excuse me. They tell us there's 11 cubes in the front and it's 6 deep. So the area of the front's 11, it's 6 deep, so that's volume of 66. They tell us there's 11 cubes in the front. So if we were to count out, I don't know, there'd be 11 if you kind of figured it out correctly. And I don't know if that's even close. I'm just doing 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to have more than 11, so I didn't draw it. But it says there's 11, and there's 7 stacks of that, so the volume would be 77. And this, conceptually, again, there's 8 in the front, 6 stacks of 8. That's going to be 48. And the volume would be cubic centimeters, cubic centimeters, cubic centimeters. So you get an idea. I'm not going to do this last one. Well, I'll just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 cubes in front. 2, 3, 4 rows. That volume would be 40. So that's a review of geometry. But now we're going to look at a cylinder. So if we have this whole cylinder, what would be the volume of that cylinder? Well, you want to count how many cubes on the base, right? So you would do, let me do it thicker. The area of that would be pi r squared. You'd have to know the radius, and that's how many cubes, if you counted all these out, it would come out to be pi r squared. Well, the height, how many stacks, you have to multiply it by the height. So the volume of a cylinder would be pi r squared to get the area of the base times the height, and that's would be the volume. Now, in today's homework, today's lesson, you're going to be taking, ooh, that's not going to make a nice thing for me. We're going to be taking a thin disc. So that thing's going to have some thickness. And we're going to call that h, in this case, delta x. And this is going to have an r for a radius. And so the volume, I should get a different color for that, shouldn't I? I'll be nice to you guys and get a color that matches better. So if you want the volume, we call this a disc. So whenever you have a thin cylinder, basically it's a disc, and the formula for volume is the same. Volume is the area of the circle, pi r squared, times the height of this, which is delta x. So same idea, but instead of saying the height, we're saying the height is delta x. So keep that in mind as we move on to volumes of revolution. So the hard part of this is to be able to visualize what is going on. So I'm going to do something for you. We want solid of revolution. Get my controls and back up a little bit here. So in this section, you're going to be given a graph. So in this case, you have f of x and g of x, and they want the region between it. They're going to rotate. Sometimes you don't have a bottom one. You're going to have it all the way to the x-axis. And you'll see we're going to do many different types of examples, but we're going to revolve it around the x-axis. So it's going to spin around the x-axis. So I'm going to take this, and as you rotate it around, you get this three-dimensional shape, okay? So you have to be able to visualize what's going on, how this is produced, and we're going to be finding the volume of this in various ways. If I can spin that. Pretty cool, eh? So we need to figure out how to get the volume created by revolving around an axis. It's not always the x-axis, it's not always the y-axis, it gets a little tricky. So we're going to get another one of these for you. This one will be solids of revolution. So this one we have, it almost looks like a sine wave shifted up and then a line, and we have a shaded region, and we're going to rotate around the x-axis again. So as we do that, as we rotate, you produce a shape. And so you can see what's happened. The original shape rotated gets us a pretty cool looking I don't know what you'd call that. Could be like a vase looking thing or whatever you want to call it, but pretty cool. So that is another example of a volume of revolution. We can go to the last one, and you've seen these. I've done these examples for you. But the last one is this one. Here is the connection. So we have a function f of x from a to b that's been rotated around the x-axis, and it produces this cool looking thing. Now, in the previous section, we added up the area of a bunch of rectangles, and we added it up by integrating. But this time, to get the volume, here's what we're going to do. This disk, picture this thing that I'm moving across are a bunch of disks. If I could find the volume of every single disk from A all the way to B and added those up, I'd get the volume of the whole thing. So instead of adding areas of rectangles, I'm going to be adding areas of disks, or volumes of disks, excuse me. And I just showed you how to find the volume of a disk. So that is the concept of this chapter. That's what we're going to be doing. So let me go back, whoopsies, to this. Here is the one we just did. So remember, you have a bunch of disks. Ooh, do I like that fill color? Let me change that. The fill should be a gold. That's orange, that's not gold. That's cool. So we're going to do a bunch of these. That's not a disk. There we go. And so throughout, again, that's not a disk. That's better, not perfect. And we keep on going till you get to the last one at the end here. And so the concept, we wanted to get the volume of each of these, assuming they all have some kind of a thickness, okay? They all have some kind of a thickness, right? And so I'm going to make it almost like a coin, you know? A little coin. Now, that has a radius, and it could be drawn, that's a radius, that's a radius, that. There's a bunch of them, but there's only one that makes sense. Let me redraw the x-axis because it is gone. There it is. The only radius that makes sense is this one. I'm going to call that my radius. And the reason that's the only one that makes sense, that's the only one I can find, because I know f of x, and I know, okay, the x-axis is the line y equals 0. Very important that you know that. Here's y equals f of x, y equals 0. I can find r by taking big Y minus small y. If I draw the radius here, I don't know what the value of y is there. If I draw it here, now we're getting crazy. We don't know what's going on. So it's obvious. And one hint for you, when you do big Y minus small y or big X minus small x in a volume of revolution, your axes of rotation will always be one of them. And then your function will be the other. So you have to know where those are. Okay, so to finish this off, the volume of revolution, we add up all these disks from here all the way across, and we lost our labels. This point here we're going to call A, and this point here we're going to call B. So add up, so that when you see the integral, again, you should see, oh, I'm adding a bunch of stuff up. What am I adding? I want to add the volume of all my disks. Okay? But how do you find the volume of a disk? A volume of a disk, we just learned, is the area times the thickness, and I'm going to claim this thickness, just like we did with the rectangles, is a change in x is dx. So what is the area of a circle? Well, I know that's pi r squared times the thickness dx. So the last step I have is figuring out r, and just like the last one, that's going to be the big Y minus the small y, and the big Y is the black line, f of x, and the small y is the x-axis, 0. So that will be f of x minus 0. So now in my final formula, I add up all the disks from A to B of, I'm going to pull the constant pi out in front, r squared dx. Oh, not r. R we found is f of x dx. And that's how to find the volume of revolution. Okay, before we go to this next example, I have another illustration for you. So this time, we're going to rotate around the y-axis. So we have the function y equals x squared, and we have a line y equals d, and the y-axis, and you get this region, but now we're going to rotate around the y-axis this way. So as I rotate it, whoa, that's weird. I don't know why it does that. Yeah, it goes that way. So that's what we're doing. You should see we're producing disks that go this way. So let me go back to here. So yeah, I'll give you the equation. This is y equals x squared. And I don't know if you can see it. Let's do it in this color. This produces disks like this. Well, let's try it again. Disks like this. Let's try it again. Disks. There we go. Mucho better. And let me fill the inside different. Let's fill it with a baby blue. Yeah. So there's our first disk. And then we're going to have a bunch of those. You're going to have a small one down here. That's crazy. Small one there. Another one. Wow. Another one here. Try it again. Third time's the charm. Yeah. And so all the way up and down, you're going to have a bunch of disks, and we have to add them up. Okay? So what's the radius? Well, it's going to go from the axis. Let me redraw this axis for you because we lost it. Here is the axis of rotation. And that axis of rotation is the y-axis, which is x equals 0. And here we have y equals x squared, which is our function. And where should we draw our radius from? It makes sense. Not here, because we don't know this function. Well, we actually do. It's y equals x squared, but you'll see we don't. Kinda. We do, but we kinda, it's hard. This is y equals x squared. That makes sense to do the radius. So you could technically do it on the other side. I'll grant you that. So my radius, I will do in black. And I told you, always goes from the axis of rotation to your function, so that should be my r. In this case, my r will be big X minus small x. Big X minus small x. So r equals, what's big X? Big X is the right side. Small x is the left side. What's x here? We have a problem. That's y. We need to solve for x. I square root both sides. And don't forget the plus or minus. Okay. What's going on here? Weird stuff. But x is square root of y. Okay? X is square root of y. And so you can actually move the plus or minus to this side. So basically, if you get a plus x or a minus x, the y's are the same on both sides. So big X is going to be square root of y. And small x is 0. So there is my radius. And then I want to get the volume. I'm going to add up the volume of all these disks, but these times these disks are horizontal. And I'm going to start at the bottom. In this case, it's 0. Right here, that's 0. It's not always 0, and I don't know what it is right here. Oh, that's 2. I'm counting lines. 1, 2. And we're going by onesies. So technically, it would be 2. And I found my r, so it's pi r radical y squared dy. The thickness of one of these disks, this time the thickness is a change in y, it's dy, because as you move up and down, y changes. So this distance is a change in y. We could actually solve this one. This one's doable. Square root of y squared is just y. The antiderivative of y is y squared over 2. And so we're going to get 2 squared over 2 minus 0. And there's our answer, 2 pi. Cubic units. Very interesting. All right, so we have 2 more examples we're going to run through. And that's the end of this video. You could try this on your own. Or if you get stuck, you can let me give you some hints. So f of x equals x squared, x plus 1 squared. That's this line. The x-axis is here, and x equals 2 is here. So here's our shaded region. X equals 0, y-axis. So you have this line, this line, this line, and this line. So this is our shaded region. I will shade that in for you because I'm a nice guy. So if they didn't give you this graph, you'd have to be able to graph this and figure it out and figure out the region. So that's R, the region bounded by those 4 graphs. We're going to rotate this around the x-axis. So here is where you have to kind of see what's going on. So here we're going to have a disk here. Ooh, I don't like the sideways one. Can I get it vertically? That's too much of a circle. Let me delete that. Here, let me try this again. So I'm going to pull. If you look, this is 1, 2, 3, 4 space up, 1, 2, 3, 4. So I'm going to go through that point right there when I do this thing. So let me see if I can get a nice disk there. That's not a disk. Try it again. See if I can get a nice disk here. Okay, decent enough. Not perfect. My first one is going to be here. Okay, my last one, I thought it was going to be bad. Let's try it again. I don't want that. I don't want the text box. Okay, let's try this last one again. Here we go. Smooth curve, bro. Smooth. No! I should have pre-drawn these for you. You know what? I can make a small... Oh, it worked. It worked. I don't have to do anything. Okay. So that's what you're picturing. Now we need to add these all up. How do I add all these disks up? So the volume would be... So here we go. How do I add them up? You integrate. And we went from 0 to 2. Those were our boundaries. 0 to 2. So we know we're going to add up the disks starting at 0, ending at 2. Now we want pi r squared, but what is r? I'll go ahead and do r squared. And the thickness of these disks is going to be a change in x. So our thickness will be dx. And what's the radius? Let me draw the axis in here again. There is the x-axis where y equals 0. This is the graph, y equals x plus 1 squared. And so where is our radius? Yes, it always goes, ooh, I need to darken that up. Our radius always goes from the axis of rotation to the graph. There is our radius. And that's going to be big Y minus small y. Oops, it won't let me right off the page. What's big Y? That's x plus 1 squared. What's small y? That's 0. So we're almost done. Pi, integral from 0 to 2. That's going to be x plus 1 squared dx. Now I just have to integrate that. Apply the fundamental theorem. Okay. This should be a rewrite. X squared plus 2x plus 1. Now it's just a bunch of algebra. X cubed. Well, first we take the antiderivative, then a bunch of algebra. X squared plus x. Okay, plug in 2. 2 cubed over 3. 2 squared plus 2. Plug in 0. That's just 0. We're almost done. 8/3 plus 4 plus 2. That's going to be 8/3, which is 2 2/3. Plus 6 is going to be 8 2/3 pi. Now, if you want to do it, it's 26 over 3 pi. Now, if this were an AP test, you would stop right there if it's FRQ. But if this were a multiple choice, the answer could appear as either one of those. So make sure you know how to simplify. And that's our first example. And we have one example left, and we are done. Dunno. And you'll have some homework. Let R be the region bounded by the curve. Okay. This is the curve. Y equals opposite of x plus 1 squared plus 8. The x-axis, y equals 0. Here is y equals 0. And the vertical axis, x equals 0. Here's x equals 0. Let me darken that up. So you see the shaded region between those three? I hope you can see that. If you can't, that's no bueno. So some of you are going to be having a hard time visualizing what's going on. You just need to practice until it all makes sense. So we're going to take that shaded region, and what are we going to do? Now we're going to revolve it around the y-axis. We're going to rotate it around here, producing disks like that. Hopefully you can see that. So let me start creating these. So there's going to be one at the bottom. It's going to go like that. Not bad, not bad. Not the best. Can I make that transparent? Can I? No. Thought maybe I could make it slightly translucent. And I'm going to draw another one. That's not working. Nope, didn't like that. Try again. I don't think my things are that bad. Whoa! Okay, I can make it bigger and shrink it down, right? I can make it bigger. Wow. Try that again. I'll just shrink it. This thing's horrible. Wow, it can't even recognize an oval. I'm having issues here. Okay, let's move it over here. There. This is pretty sad. Pretty sad. Okay. Now let me, in a dashed line, draw this other side so you can kind of see. And can I make that? No. Let me just make a dashed line. Yeah, you kind of see what's going on. So hopefully you can see. Yeah, that is a rough time on that. Hopefully you can see what's going on. So what's the volume of this? Now, you can pause and try this. The volume will be, you add up all the integrals. Now, where are we starting? We're starting here at 0. And where's the last disk? The last disk would be right here. And what is that point? Well, x is 0 there, right? X is 0. If you put a 0 here, that's going to be 8 minus 1. That's going to be 7. We know that point is 7. So we're going to add up all the disks from 0 to 7, and it's pi r squared dy. Why did I put dy? Because the thickness of this little coin or this disk is a change in y. As you move up and down, it's a change in y. So what's our radius going to be? That is the question. So here is my r, and in this case it's going to be big X minus small x. So r is going to be big X minus small x. The question is, what is big X? Big X is right here. Small x is right here. So I need to find big X. The problem is, on the big X, I know this, but that's y. I need to solve for x. So let me subtract 8 from both sides. I don't like the negative sign. If I multiply both sides by negative, I get this. Let me square root both sides. Now technically I need a plus or minus there. And let me subtract 1 from both sides. So 8x equals negative 1 plus 8 minus y, or it's negative 1 minus 8 minus y. So here's what's going on. This number is bigger than this number. That's the bigger x, that's the smaller x. So for every value of y, you have a big X and a smaller x. This side, the right side, is this. The left side is that. So that's what's going on. So we are going to use this one. That's our big R. Wow, this was a lot crazier than I anticipated. The good thing, the small x is 0 because x equals 0 on the vertical line here on the y-axis. So our final answer, I would get negative 1 plus 8 minus y squared, because it's r squared, that's my radius, and it's going to be dy. I am not going to integrate this. Put it in your calculator and get an answer, because this integration gets kind of ugly. Because first I have to square that, and then I have some u subs to do. It gets ugly. I'm not going to do that. I am done. This is it. So hopefully you understood that. Bye-bye.